Good morning, students. I hope all of you are in best of your health and spirits, particularly in this COVID-19 pandemic situation. So, moving ahead in our course on the application of spectroscopy to inorganic systems, today I am going to discuss Mossbauer spectroscopy, which is which is the first part today, uh, which it will be introductory in nature. So, what we have seen so far, we have already covered a lot of the spectroscopic techniques that involves light matter interactions, that is starting from microwave spectroscopy, infrared spectroscopy, going higher in the energy levels in terms of electromagnetic energies. Uh, we have also discussed the UV visible photoelectron spectroscopy, X-ray photoelectron spectroscopy, and as well as not to forget the Raman spectroscopy, which is another type of vibrational spectroscopy. And so, moving ahead in the electromagnetic spectrum in terms of energy, we today we will be discussing this emission of gamma rays and absorption of gamma rays. That is what is covered in this topic called Mossbauer spectroscopy. So this Mossbauer spectroscopy is particularly a very fast event that takes place. The Mossbauer effect that happens that was discovered, and it takes place at a it is a very rapid event in the sense. So this takes place at the time scale for this event is the absorption of gamma ray is about 10 to the power minus 18 seconds, which is much faster as compared to what we have seen in the electronic spectroscopy. That was about femtosecond, on the order of femtoseconds. But here we are going to the uh, once even faster. We have the process is becoming even faster. That is attosecond, you can say. That is 10 to power minus 18 seconds. So so Mossbauer spectroscopy is a versatile technique that can be used to provide information in many areas of science. It is nowadays used in biological, determining the iron's environment in a protein. It is also used in metallurgy to know about the oxidation states of the iron that is present. And in chemistry, there's many more applications, such as various complexes, coordination complexes in organometallic compounds, that particularly that of iron, which we prepare, and if we want to know this, some aspect of electronic structure, or we want to know the oxidation state, chemical state of the system, it is very helpful. So it gives very precise information about the magnetic and time-dependent properties of materials, uh, besides chemical and structural properties. So this is particularly unique. You get magnetic properties at a magnetic information about the local environment present around the nucleus. And key to the success of technique is the recoilless gamma ray emission and absorption. We will learn more about that. We will have a full discussion on what is the recoilless gamma ray emission and absorption. This effect is referred to as Mossbauer effect, which was discovered by Rudolf Mossbauer. So it is in his name. The effect is called Mossbauer effect. It is so this was the work of Mossbauer, which in 1957, which got him the Nobel Prize in 1961. And the discussion, so the discussion in this entire Mossbauer spectroscopy that I am going to discuss will be composed of three sections. Three sections. Only the first section will be discussed today, that is the introduction, and the next two sections will be discussed in later classes. So today I am only covering this Mossbauer effect, the theory behind it, and next we will see how we can use it, this technique, to investigate the systems, how we can probe different atoms, molecules, or solid matrix, and know its the oxidation state, the magnetic environment present within the system. So the Mossbauer spectrum, and then we will finally discuss some of the typical spectra of complexes and other compounds which have and what are the principal factors that affect their spectrum. So coming back to the very basics of Mossbauer spectroscopy, we need to understand what is gamma ray. As you know, the gamma ray is emitted by a nucleus, which is an unstable nucleus, which is having excess energy. And energy is when nucleus is in excited state, it tries to go back to the ground state, and in this process, it releases energy in form of photons, in form of electromagnetic radiations, that is called gamma radiations. Okay, so this is the typical nucleus. If we can visualize it, this is a nucleus composed of neutrons and protons, and the gamma ray is given off. So basically, if you are looking at the nuclear structure, you have an excited state of nucleons are in an excited state, and then when this nucleon tries to gain stability, goes back to the ground state, and in the process it emits radiation of equivalent energy that the two states are showing here, and so this energy is given off as gamma rays, gamma radiation. So we have original nucleus, which may undergo alpha or beta decay and the new product nucleus formed is in excited state. As it tries to regain stability, it emits excess energy in form of gamma rays and reaches the ground state. That's the picture is showing over here. Taking an example of cobalt 60, you can see here cobalt 60, which undergoes beta decays, two type of beta decays you can see. So both of them landing up the product nuclei is landing up in a excited state. In one case it is 0.31 MeV. In the other case the difference in energy is 1.48 MeV from this cobalt nucleus. So this is the energy which is given off as beta radiation, beta particle. And so after this, so this excited state is unstable, and within the nucleus, within the new nucleus formed, that is nickel 60, the excited state loses energy in form of gamma radiations and gains stability by coming to the ground state in this manner as shown over here. So the nuclei can undergo a variety of energy level transitions, which we have just seen, which can be emission or absorption. So usually when we discuss nuclear chemistry, we have talked about radioactive decays. That was basically emission of gamma rays. When we talk about so that was emission of gamma rays from radioactive source. This is what you have studied in very earlier classes in 11th, 12th and at bachelor's level. Now, so these energy levels are influenced by the surrounding environment, both electronic and magnetic, which can change or split the energy levels. So these energy levels provide information about the local environment within the atom, and this aspect has to be taken care of. This is what we want to investigate and we want to find out by this spectroscopic technique that we are discussing. So there are also if we want to gain the information about local environment around the nucleus, we also find there are some interactions with the electrons. There are electrons present in the nucleus because as you have seen in your quantum mechanics classes, that the electrons in the s orbitals have maximum electron density at the nucleus, so that interaction with s electrons affects the system, and those things. Um, some of these will be affected due to the bonding situations around that nucleus. When that atom takes part in bonding, and that electron density changes, the s electron density changes, and you will have some those interactions. These are going to affect the transitions, nuclear transitions that will take place, and we will just try to understand in more detail about each of the things. And then there is something called also the recoil of the nucleus when gamma ray is emitted. So this is this is an important thing. We are talking about recoil of the nucleus. So what do you mean by recoil? Have you can see a gun. If you just can imagine a bullet being fired from a gun, then in many cases you will find that you can see. So as the bullet goes away from is ejected out, there is a backward push that the person gets, and this is what we mean by recoil. There is opposite movement of the gun, and that is a recoil. This is a recoil effect, recoil that we are seeing, and this is happening due to what we call as the conservation of momentum. This is so as the bullet goes away from the gun, it is ejected out, and the whole system undergoes a recoil. It moves in the reverse path, reverse way, and this jerk that you get is the recoil. Okay, so this recoil. Now imagine that instead of this gun, you have a nucleus, and instead of this bullet, you have a gamma ray photon that is ejected out. So gamma ray photon becomes your bullet, and the nucleus is your gun. So the behavior will be exactly in a similar fashion, that as a gamma ray photon is ejected out, there is a recoil, a massive recoil in the nucleus, because of which the energy will be energy of the gamma ray can get affected. So this is what we have to visualize, that emitted gamma ray has energy which will be reduced by the recoil energy. So this is a nucleus which emits gamma rays, and suppose the nucleus was moving in this direction, gamma rays, now photon is emitted in this direction, then because of the recoil, there will be reverse movement of it is possible that the nucleus moves in the other way. Okay, so what we will energetically, if we so this is what the picture that you can correlate with the previous picture, the gun and the bullet. So gamma photon and the nucleus behave in a similar manner, and emitted gamma ray has an energy reduced by an amount ER, which is the recoil energy. So which is so the component nuclear transition so as compared to the nuclear transition energy, the energy is reduced. So nuclear transition energy, we are talking when we say nuclear transition energy, we are talking about the energy as per theoretically, as you calculate from the energy level difference, the difference between two states, excited state and the ground state, that is your nuclear transition, theoretically what you calculate, and the actual energy of the gamma ray that is emitted is different, and that it is different by an amount of ER, that is recoil energy. So this is the case. Now suppose if you place another nucleus which has exactly of a similar atom of a which has such that you theoretically you have calculated the energy levels match, so that the gamma ray, if it is emitted, should be absorbed by the another nucleus in the ground state of the same type. But as this emitted gamma ray has energy less, reduced by a factor of ER, for the absorption to occur, that is for the energy, both the energy to match the requirement for absorption and the emitted gamma ray energy, both must match, and so you must increase the energy by ER amount, then only the absorption can occur. So to achieve this resonance condition, that the loss of resonance, the loss of recoil energy must be overcome. You have to compensate for the recoil energy that is that comes in over here, that we have just seen. So moving ahead, so we will like to discuss, so we should discuss this in more detail. As you can see, this is suppose our nucleus before emission of gamma ray, and this is the nucleus after emission of gamma ray. So you can see the gamma ray is going away, and suppose the energy gap between the ground state and the excited state is E, as given by this EE minus EG. So now you analyze this situation. Suppose this nucleus, suppose the system that we are discussing, the atom that we are discussing, it is in gaseous state. So this is the nucleus is in random motion in three-dimensional space with a velocity. So for the simplicity, we let's consider only the x-axis. So velocity along the vx will be vx along the x-axis. Let's consider that the motion is only in the along the x-axis direction. So if this is the vx, then after emission the velocity will be changed, and another there will be additional term of plus v. This is the velocity imparted due to the recoil movement that occurs, recoil momentum, that is to conserve the momentum of the system. There is recoil, and that affects this velocity, and this added component of the velocity is v, which can be negative. Okay, so this is a vector. You should know that, and usually, as we have picturized in earlier slide, and it is opposite in direction to the gamma ray photon. So energy will be, if suppose the energy is E, is the gap between two energy levels, excited state and ground state energy of the nucleus. So E plus because the atom is in random motion, so the kinetic energy half mvx square. And so if you apply the principle of conservation of energy, then this energy, the energy before emission, should be equal to the energy after emission. So as the after emission, we have the gamma ray energy, which is E gamma emitted. So energy of the gamma ray, E gamma, plus half this kinetic energy of the system, which is m. M is the mass of the nucleus, and Vx plus V square is the. So this gives you the energy of the system after emission. So these two terms must be equal to each other. Similarly, momentum must be conserved, and it is the conservation of momentum due to which the recoil is occurring, to conserve the momentum. So this mvx, initial momentum of the system, should be equal to the final momentum of the system, and final momentum of the system can be you can simply place the motion of this nucleus. You can, from the motion of the nucleus, you can make out that this will be the contribution to the momentum due to the movement of this, including the recoil. And the other part is the momentum that is carried away by the gamma ray photon. So this is simply, if you are considering the Einstein's relation, E is equal to mc square, you can easily arrive at this equation, and this form of the momentum that we are discussing here, E gamma, energy of the photon by speed of light. So we are considering the isolated atom, the gas phase, and we have calculated the difference in energy between the gaps. to state the following treatments refers to the so we are treating this in one dimension only, the recoil movement for simplicity. So simplification causes it will not cause any loss of generality as the components of motion in other two dimensions remain unchanged. Uh, if the photon is emitted with a nucleus M, so this is the description that I have just already discussed in previous slide. I have already discussed this part. This is just a write-up so that it also serves as a notes for you. So this is the same thing that I have already discussed. I am not going to much of the details. I have already discussed this. So V is vector and it is opposite. This is the point that you have to remember if you want to apply this concept in a good, in an efficient manner. So total energy of the system is this, which must. So this is the equation that we get. It is a very important equation from the conservation of energy. The difference between the energy of the nuclear transition E and the gamma ray photon will be, let's denote it as del E, E minus E gamma. So the theoretically calculated difference. So this is the difference between your theoretical calculation. You draw the energy level diagram, calculate the excited state, ground state energy difference, that is E, and you so the actually if there is no other motion taking place of the nucleus, if there is no recoil, then gamma ray energy should have been exactly the same as E. But now, as we know now, that because of recoil movement, the gamma ray energy has been changed and it is E gamma. And this difference between the theoretically calculated energy difference and the energy of the gamma ray is del E. So you can further analyze this equation. You have so substitute this. You can so you have you can place these values E minus E gamma from here. You can get this E minus E gamma. You can rearrange this equation and you can get the E minus E gamma term here, half mv square minus this. You will get this. So if you are able to rearrange this equation, substitute the value of E gamma here, you can get up to this equation. And what we are getting here, this term, these two terms, now we define a new term here, the recoil energy. We have got the expression for the recoil energy. This half mv square is equal to the recoil energy, the small component of velocity added to the nucleus after as a result of recoil is V, and half mv square represents the recoil energy ER. Similarly, the other part that we are seeing here, mv into Vx, this term gives us the energy, we call it the Doppler effect energy. So we have the recoil kinetic energy, we have also got the Doppler effect energy. Doppler effect we have already studied in your class 12th, 11th, 12th class thing. Just like a siren, if a ambulance is moving with a blaring siren, you will, as it moves towards you, you have you hear the sound's frequency increases because there is additional component of the due to the velocity of the vehicle. And if it moves away from you, as it goes away from the frequency decreases. So that is the Doppler effect that we know. So this is due to the movement of the vehicle. In a typical case, the sound waves have so Doppler, there is slight increase in the frequency of the sound wave, increase or decrease. So similarly, consider this nucleus as a vehicle and gamma ray as the photon radiation that is being emitted. So its frequency is also going to get affected due to that reason. So gamma ray energy thus differs from the nuclear energy level separation by an amount which differs. So the separation, so gamma ray energy is different from the nuclear energy level separation, theoretically calculated one, by an amount which is equal to the ER. So two things, there is ER term and the ED term, that is Doppler effect energy, recoil. So there is one term, recoil kinetic energy, which is independent of atom velocity, and the ED term which is dependent on the atom velocity Vx. So these are two things that is affecting the gamma ray energy. The gamma ray energy is different from what you calculated from the nuclear energies level separation. So the mean kinetic energy for each of the translational degree of freedom of a free atom in a gas which is undergoing random thermal motion can be given by so it is given by this equation. So the mean kinetic energy is this, which is half mv square x. So this is the mean velocity, root mean square velocity. Mean square velocity, velocity means square velocity along x-axis. And K is the Boltzmann constant, T is the absolute temperature. So this is something that you already know as applied to gaseous atoms. So this is this simple principle taken from there. So now you can calculate further from this equation. You can calculate this the root mean square velocity. Mean square velocity is Vx, and with bar over here, and then if you take it under root, that is gives you the mean square velocity, which is equal to ek. Sorry, the k has to be subscript over here, 2 ek by m. And so if the calculations will give you you can substitute the value of Vx in this the value of, in terms of kinetic energy of mean kinetic energy of the atom. We can express the mean square velocity in terms of the kinetic energy of the atom, the nucleus undergoing the motion. And so if we replace this term in terms of 2 ek by m, we get this k is subscript e, this means kinetic energy. It is so if you do this, then what we will obtain is an equation which is under root 2 ek mv square. So this mv square is the recoil energy we have just discussed. We can make it. So final expression is this: your Doppler effect energy is equal to twice under root kinetic energy, mean kinetic energy per translation degree of freedom into the recoil energy. So you got the two parts clearly spelled out in terms of. So there was ER and ED, the two terms which were affecting the gamma ray energy as compared to the actual nuclear transition, and the ER was one factor due to recoil of the nucleus. Then there is another thing that is that is the Doppler effect energy, and the Doppler effect energy also depends on the recoil energy. So this is the thing that is important, and it also depends on the mean kinetic energy. So thus now you have the clear picture. Thus referring to the equations, del E is equal to ER plus ED. This is one equation. Then you have also found the ED, the Doppler effect energy. Mean Doppler effect energy is this. So based on these two equations, we can say that the gamma ray distribution is displaced by an amount ER. The gamma ray energy will be displaced by an amount. So we will have number of photons emitted. We will have variation of recoil energy, there will be spreading of the energy due to the Doppler effect, and there is displacement of the energy. So the kind of there's a Gaussian distribution profile that you get if you analyze this part. So this is E, the theoretically calculated energy level transition energy, the nuclear transition energy. Now this nuclear transition energy gets, if you are analyzing say 100 such atoms under whose nuclei are giving out gamma rays, photons continuously. So if you analyze them, then what it means that given a population, you will have distribution of gamma rays energy, which is giving a Gaussian profile like this. So the original energy E is displaced by an amount, this, which is shown over here. So the displacement, it is causing a displacement by an amount, this from this line, original line of energy, it is displaced, it is to the left side, that is, it is decreased E minus ER by an amount ER, that is recoil energy. And the Doppler effect, the ED part is shown over here, that it will be spread out from the mean position in plus ED on this side, minus ED on this side. So there will be a total spread of two times the ED. So this is how pictorially, in this graphical fashion, we can show the relation between E and the ER and ED. Okay, so this is the profile that we have discussed for an emitting nucleus, a nucleus which is emitting gamma rays. Now, so a typical calculation will tell you that for E and E gamma having values of 10 to the power 4 eV, the ER and ED will come out to be of the order of, so 10 to the power minus 2 eV, and this is a typical calculation for iron 57 Fe, that is which has a first excited state at 14.4 keV. So this is a difference that you must spot out. You must pay attention to this part. The gamma ray energy are on the order of 10,000 electron volts, 10,000, 10 to the power 4 electron volts. Whereas for electronic transitions, you were having energy levels which was a few eV. So if you, for example, if you consider the visible energy, you have already performed UV visible spectroscopy. So if you from 400 to 700 nanometers, if you analyze the energy in EV, those electronic transition involved only 1 to 3 EV. Whereas here we are talking about 10 to the power 4 EV. So this is a huge energy difference between the energy level transition for electrons and energy level transitions for nucleons. So this is the things that so when we have 10 to the power 4 eV as the nuclear transition energy difference, then the recoil energy of the earth 10 to the power minus 2 eV. And in a similar fashion, if you calculate for UV visible, you will find that there will be a recoil over there, but that will be too insignificant. You will have, and this ER will come out to be on the order of 10 to the power minus 10 electron volts in case of UV visible and ultraviolet UV visible spectroscopy, that is electronic spectroscopy that we are talking about. So that is insignificant in case of an electronic transition, but in a nuclear transition we have to consider, because now this is significant. This is a very high value because the energy involved is much higher. We are by a factor of 10 to the power 4. So so we have to consider the recoil here. So okay, and it is so the values of ER and ED can be expressed in terms of gamma ray energy, and so if you try to calculate the recoil energy in terms of gamma ray, you have half mv squared that you have defined, So this can be written as p square by 2m, the momentum by the mass, momentum square, and um, so recoil momentum is p here, and m is the mass, and p gamma becomes the if we so this recoil momentum p must be equal and opposite to the p gamma, that is gamma ray momentum of the gamma ray. So you can simply analyze this. Momentum of the gamma ray was E gamma by c, so the recoil momentum can be also equal to this with a negative sign, okay, minus E gamma by c. So this is your recoil momentum in terms of gamma ray energy, and this is the recoil energy. If you have obtained the recoil momentum, then p square by 2m, you substitute here, you can get the recoil energy in terms of gamma rays, that is E gamma by c 2mc square, E gamma square by 2mc square. So now we have found an expression of ER, the recoil energy, in terms of gamma rays energy, that is E gamma square by 2mc square. Next, from this, moving ahead, we have the expression for this Doppler effect. Similarly, we can also have, as we have derived the expression of recoil energy in terms of energy of the gamma ray. Similarly, we can also derive an expression for the Doppler effect Doppler effect energy, that is given over here. So it is possible to derive this thing, and it will be under root E gamma under root 2 ek, the mean kinetic energy of the atoms, the nucleus that is undergoing, the nuclei that is undergoing motion, and divided by M.Sc square, that is c is the velocity of light. So we can we have now developed a system, the fundamental, the background, based on which we can discuss the gamma rays emission and the resonant absorption. So the fundamental radiation theory is that, as we know, in terms of, we have already dealt with UV visible absorption spectroscopy, infrared spectroscopy. So we all know about it, that the proportion of absorption is determined by the overlap between the exciting and excited energy. Okay, so you want to be a perfect match of the exciting radiation and the required energy for the the incoming radiation and the excitation energy gap as per your calculations from the energy level diagram. So these two must match together. So in this case also, the gamma ray has lost energy by an amount ER, that the recoil. So that gamma ray energy must be increased by an amount ER, so that only then it will be reabsorbed by a nucleus. In another way, we can say that for the reverse process to occur, the gamma ray to be reabsorbed by a nucleus, if we place another nucleus which is in ground state, that will happen only if the reabsorption will occur only if a further increment of energy ER is provided. Okay, so that is we also say that we must provide the energy, gamma ray energy, the nuclear transition energy, and plus the recoil energy as well to the absorbing atom. So we have already discussed how the profile looks like when an atom or nucleus is emitting gamma ray photon. It's the spread of energy is like this. The actual calculation is this one, E, and it spreads out like this in a fashion, in a Gaussian distribution profile, which is, and the total spread of the energy is 2 ED. So this was for emission of the gamma ray. And similarly, you can also analyze the absorbing nucleus, which is in ground state, and it absorbs the gamma rays. So you'll find that if it is also in gaseous state moving around, it will have the distribution of energy will be given by this. In a similar fashion, we can find, as we have done for the gamma ray emitted by a nucleus, we can also find the gamma ray being absorbed by a nucleus which is in ground state and moving randomly in thermal motion in gaseous phase. So in that case, we will have a spread, and a very small area which is shown by shaded red region represents the area where you are getting a perfect match, the overlap. So here the energy will be absorbed. If your energy level profile is matching with the emission profile, absorption profile is matching each other, and the absorption again. This is what we call as resonance. Resonant condition has been achieved, and the absorption will occur. Okay, so so to produce a resonant signal, the resonant absorption, the two energy need to overlap, and this is shown in the red shaded area. This area is shown exaggerated. Actually, it is even less than this. If you are considering a gaseous nucleus emitting gamma ray, a gaseous atom absorbing gamma ray, if you have a collection of these nuclei, then the profile will look like this, and this shaded area is actually 1/1,000,000th, even much less than what has been shown in the diagram, and it is then it becomes a impractical technique. The signal will be too weak and you can't observe anything. This is not this will be a kind of signal that you can't detect. Simple. It is impractical. In a gaseous phase, emission of gamma ray, absorption of gamma ray is it will be very, very difficult to detect. Almost it is impractical, as we say. So typical values of what it could look like is this given over here. E gamma is 10 to the power 4 in case of iron, that we have discussed earlier also, and if we consider the mass as 100 AMU for typical typical nucleus, it is found that the recoil energy is of this order, 10 to the power minus 4 eV, and in Doppler effect value, the energy due to the Doppler effect, this is 10 to the power minus 3. So minus 3, 10 to the power minus 4. This is what you get at room temperature. The amount of resonance overlap in this such case that is already shown over here in the shaded region. So here is the breakthrough that Mossbauer got, Mossbauer could achieve. So he said that the nucleus, the emitting nucleus and the absorbing nucleus both must be in a solid matrix. You have to embed those nuclei in a solid matrix so that the recoil becomes as low as possible. So what happens is that if they are trapped in a solid matrix, then the matrix, because there is no linear energy transfer, there is no linear momentum transfer of momentum in form of linear momentum of the atom alone. It is the entire mass, entire crystal, which is much more massive than the one single atom. This has to move. It will be used in carrying away the recoil momentum. So the movement will be very, very less. And so the gamma ray energy, for which we were getting so much fluctuations, the spreading of energy that was there, that will be minimized. That will be effectively minimized, and then the absorption will occur. We will have a greater chances of absorption taking place, and then the signal could be detected. Absorption signal you will be able to detect absorption signal. So the recoiling mass is now effectively the mass of the whole system. If you embed it, even if you consider a single You know, in laboratory you take out a single crystal from the box from the bottle. That single crystal also contains 10 to the power 15 atoms. So 10 to the power 15 atoms in a single small crystal of micron size, and so the recoil energy for that also will also become very low. This whole 10 to the power 15 collection of atoms will behave as one unit, and they will recoil together. So entire recoil momentum will be carried off by this bunch of 10 to the power 15 atoms. So compared to one atom, the movement will be much less, and the energy that will be carried, ER would become very less, and so gamma ray will be almost the same, very close to the nuclear nuclear energy transition value, which we calculated from the theoretical energy level diagrams. Doppler effect will be also minimized because ER has been minimized. We have seen that ED also depends on ER, so ED will be also very small. And now you can have a resonant absorption. The chances of getting a resonant absorption by another nucleus which is in ground state is more. So if the gamma ray energy is small enough, the recoil, so there are 2-3 things that we have to consider. First thing, place the nucleus in a solid matrix, 1, and 2, as we have seen, the recoil energy also depends on the gamma ray energy itself, the nuclear transition energy itself. So if we are talking about certain nuclei which are having very high gamma ray energy for the nuclear transition, then the recoil energy is going to be high in that case. For certain others nucleus where for certain other nuclei where you have the gamma ray energy is low, the nuclear transition nuclear transition energy is low, the recoil energy will be lower. So a lower recoil gives you a better chance of the emitted signal to be absorbed. So 2 things: place the system in a solid matrix, make the whole system solid matrix recoil as 1 unit. So that will be practically also brought about to be 0, the recoil thing, and the gamma ray energy will also have to be low to avoid the recoil effect. So usually we have observed this kind of spectroscopy which we perform in Mossbauer spectroscopy. Only those transitions are taken which have lower gamma ray, and the energy gap is less. Amongst the various types of gamma rays, the lower energy gamma rays are more likely to have a recoil free event during the emission and absorption process. So they will give out, so this situation, when you achieve this kind of situation, if the emitting and absorbing nuclei are in the solid matrix, the emitted and absorbed gamma ray is of the same energy, you have a resonance condition is achieved, the absorption will occur and the signal will be detected in a good numbers. You will get a good counts of gamma ray photons at the detector. So here it is important. What we have seen so far, that atoms placed in the solid matrix have much greater effective mass. The entire thing recoils as a 1 unit, and that you have minimized that 1. So recoil mass of the nuclei becomes recoil mass of the entire matrix. Now in this table, what we have shown over here, this is the range of gamma ray energies, 10 to the power 4 to 10 to the power 5 eV, which is used in Mossbauer spectroscopy. So these are typical gamma rays which we consider as low energy gamma ray radiations. And this has been compared with the chemical binding and lattice energy. In a solid, you have having lattice energy and chemical binding. that is bond energy, bond formed between within a molecule, and the lattice energy due to closed packed structure. So those things correspond to a level of 1 to 10 eV. This was what I was talking about earlier, that when I said that electronic spectroscopy have energy in the range of 1, so 1 to 3 eV that we could calculate in case of UV visible spectroscopy. And the free atom recoil in the gaseous state that you were comparing, that was on the order of 10 to the power minus 1 to 10 to the power minus 4 eV. Lattice vibrations is on of this order, 10 to the power minus 3 to minus 1 eV. So now let's consider two important things here. In the Mossbauer experiment, we have to consider we need to account for two important things, that is recoil momentum and nuclear transition energy E. So recoil momentum, as we say, so the recoil momentum that so we are going to account for two things, recoil momentum and the energy, gamma ray transition energy E. Recoil momentum is the when we are considering the atom, the nucleus is embedded in the solid matrix. So we are talking about a tightly bound system. The atom which is undergoing this kind of nuclear energy transition, that is tightly bound within a large matrix of solids. The free nucleus has a recoil energy of 10 to the power minus 1 eV. This energy is, so this particular energy is insufficient to eject the atom from the lattice, because it is much higher order, 1 to 10 eV, right? So this energy is what we are talking about, because if that atom has to be ejected, if you want to transfer the momentum as a linear momentum to the atom entirely, that particular nucleus, then you have to give this amount of energy. The recoil energy is only of this order, so the atom cannot be ejected out, it is insufficient. So what happens is that the transfer of momentum transfer in form of linear translational motion of the nucleus is prevented. Okay, so the only option, and the second thing is that the lattice vibrations cannot take up the momentum, because a time average of is 0. So because the recoil takes a longer time, the lattice vibrations are much faster. So the averaging effect, if the momentum is recoil momentum is transferred to the lattice vibrations, that will be 0 for the during that time of recoil, the actual recoil that was happening. So this lattice vibration cannot, so the simple thing is that the lattice vibration cannot take up the momentum, the recoil momentum that is generated. So the only way this has to be compensated, this has to be adjusted, is through the motion of the crystal as a whole, and that is too massive, and so we are bringing down the recoil energy to effectively very less value. Similarly, the nuclear transition energy E, this has to be conserved, and it can be shared between the energy of gamma photon E gamma, lattice vibration, translation kind. So these are the options that we have: kinetic energy of the individual atom, kinetic energy of the solid as a whole. Third and fourth possibilities are ruled out. Third, because of the the reason that we have just discussed in case of recoil, because high chemical binding energy, by high chemical binding energy, and the fourth can be shown to be very small. The translation and kinetic energy of solid as a whole. So the gamma ray transition energy is thus shared between the gamma ray photons and the lattice vibration phonons. And because of the quantization, now you all know that in the vibrational energy levels, the vibration energy is quantized in case of lattices, and because of quantization, you can have only certain values of energy that can be transferred, like 0 h cross omega and like that. So only if a fraction of events will occur which will have no change in lattice vibration. So there is a likelihood that because of the quantization conditions, there are some events, not all values of energy can be transferred to the lattice phonons, lattice vibration, and there there will be some events which will occur without any transfer to the energy transfer to the lattice phonons. So that will be called as zero phonon transitions. In such case, the E, the emitted energy, the E is the nuclear transition energy, will be equal to the that is the requirement for the absorption as per your calculation with for the nucleus in the ground state. The requirement to go into the excited is this E, represented by E, and E gamma is the nucleus that is emitting gamma ray photon, so the energy of the gamma ray photon. So in such case, where lattice vibrations, there is no change in the lattice vibration, zero phonon transition is taking place, we will have there is a likelihood of this this E will be equal to E gamma, and the resonance condition will be achieved. So a cobalt the Mossbauer spectroscopy so far that we have discussed is basically it is sensitive it is basically a gamma ray absorption, a resonant absorption of gamma ray, and the source of gamma ray is also a nucleus. The emission of, so we have to consider the emission of gamma ray first from our source, and then the resonant absorption by another nuclei. So this example is here, the example of cobalt 57, which decays to the 57 Fe by which decays by to 57 Fe, and so we have formation and there's two transitions taking place over here. 9% undergo this transition to the 14 to the first excited level, and rest 91% go to directly to the ground state. So this part is not useful for us. This one is useful because this 9% which is lying at this first excited level will undergo they will, when they try to come back to the ground state, see this blue line, they will emit gamma radiations which will be equal to 14.4 keV, and this gamma ray photon, if you place another iron atom here or it can absorb that radiation, so we can have absorption profile will be observed. So so that to happen, what we design, because we have to take into account the recoil energy, what we do, we keep this, the source, cobalt source is taken in a solid matrix, and then it is a carriage in device, moving like a vehicle, it is moved back and forth about its mean position, so that the recoil, you provide the energy E plus ER that we discussed, you must provide that much energy, and then the absorption will occur in the sample, because if it contains iron, Fe57, and then absorption will occur. So this is a layout which we have shown of the Mossbauer spectrometer, simple, in a very simple way. The speed of carriage is adjusted until the Doppler shifted frequency of the emitted gamma ray matches with the corresponding nuclear transition in the sample. So to take into account the recoil, although we have minimized it, and to take into account the Doppler effect, Doppler frequency shift, we devise this carriage and keep it moving, and at some movement, at some velocity, we will observe absorption of the signal. So this is another look at how the carriage is designed. This is so we have a plus. So if you, this is a reference point, you have a plus V in this direction, minus V in this direction, and here is the absorber, the sample. This becomes the source. This is the absorbing species, and here is the detector, and you observe a spectrum like this. Wherever there is absorption, the gamma ray photons, the detector is receiving gamma ray photons. When there is absorption, there is a decrease, so you observe a dip. So the typical gamma ray spectrum is plotted as a number of photons on the y-axis versus velocity of the carriage on the x-axis. Actually, this velocity corresponds to the, if you look at this carefully, it corresponds to the change in energy of the gamma ray, different energy of gamma ray, slight change in the gamma ray energy, and this velocity is usually mm per second, very small, millimeter per second. And so different gamma ray energy is required for different, if the environment here is different, um, uh, if magnetic or electric environment around the nucleus is different for iron, we will have absorption at different positions. If it is so this is a view that we have. So this is how the carriage moved, and the sample absorbs these signals. So at a particular point where the gamma ray energy is matched, this and the Doppler shift has been taken into account, and the gamma ray energy matched at some position. At that particular position only, at that particular velocity of this vehicle, will absorb a negative peak, and these are Mossbauer peaks that you are observing. Okay, so in a simplest case scenario, we have the absorbing species and the emitting species, both are exactly the same. We say that they are identical. If they are identical, just as we say that usually it is a cubic, in fact you know cubic closed packing and all that. So if you have, if it is in a cubic environment, identical atom, so iron atom in excited state emits gamma rays, iron at Fe57 in ground state absorbs the nucleus, and this is a you will obtain a spectrum which will look like this. At almost nearly zero velocity, you will get a single peak, only one peak. But in other cases, if the environment, if that Fe, say it is hemoglobin that you are analyzing, that will be a different situation around that Fe nucleus. There will be different environment is different because of the bonding situations it has, and that will affect this position. The resonant condition will change, and you will observe a spectrum at different positions from this. So those are things that we will discuss later in our next class. And so far we can say that this is a periodic table which gives you the overall idea how many elements are active, Mossbauer active. These are all the elements which are Mossbauer active has been written with red fonts, and the shaded black regions show that these are the most prominently used these days in the Mossbauer spectroscopic studies. Iron सबसे ज़्यादा use होता है, iron, ruthenium, iridium, and Sn. Tin is also used to a good extent. So as resonance only occurs when the transition energy of the emitting and absorbing nucleus match exactly, the effect is isotope specific. The relative number of recoil free events that we are talking about. So we say that we are trying to achieve a recoil free event. So we have so instead of taking the atoms in a gaseous phase, we are taking in a solid matrix, make it tightly bound to the system so that the whole system recoils as a recoils together, and the recoil momentum that we were having, it will be very, very less. So the relative number of recoil free events is strongly dependent on the gamma ray energy. So this point I have already pointed. This point I have already discussed in earlier section, that recoil energy depends on the gamma ray energy. So higher the value of gamma ray energy, greater will be the recoil energy. So for Mossbauer effect to be observed, it is desirable that gamma ray energy is as low as possible, and then only it is the spread that overlap region in the two peaks that we are getting will be more, and the process will be more effective. It will be easy to detect with the tools that you have, the instrument that you have. So for low-lying excited states, so we typically say that isotopes with very low-lying excited state, this is one condition. This periodic table is showing a lot of nuclei which are Mossbauer active, and one of the conditions for them to be Mossbauer active is that they must have isotopes with very low-lying excited states. The second condition is also about the resolution is dependent upon the lifetime of the excited states, and these two factors taken together will limit the number of isotopes that you can use for Mossbauer spectroscopic studies. So most useful amongst all these is Fe57, which has both a very low energy gamma, very low low lying excited state, and long lived excited state. So long life of the excited state, low energy of the excited state, these are two essential requirements for for Mossbauer spectroscopy to be observed. Okay, so because this iron 57 match gives it conforms to both your requirements, it is widely used, and we can observe the information about related to bonding situations in different complexes or biological species or minerals using this Fe57 source. And there are many uses of this Mossbauer spectroscopy. Even on Mars, there's a small miniaturized Mossbauer spectrometer has been sent. So this is what we come to an end of this first part, and in the second part we are going to talk about the spectrum, different types of spectrum that we obtain. We will talk about isomer shift, we will talk about quadruple splitting, and the magnetic hyperfine splitting. So that's all for today. Bye.